has mostly taken the day. It's on the cover of Nature and so on. But Brian Metzger will be sure to point out that it turned out that the luminosity of the event that was discovered with this neutron star merger, the kilonova, was indeed about 1,000 times brighter than a typical nova. So, okay, so we're getting near the end. I'm going to finish up with some discussion of kilonovae, and in particular the recent event that we observed. Svi gave some background into it yesterday, and I'll kind of rehash a little bit of that and then talk a little bit more about the observations and light curves. I'm not saying so much about the gravitational waves and the gamma rays and all the other interesting things that go on. There's so many stories to tell, and you can only do so much. But I'll kind of couch it in this broader question of the origins of the elements that we've heard a little bit about. And actually, this is a good way to kind of summarize a lot of this conference about where all the elements we observe in the universe came from. So we've heard about sort of every little piece of the puzzle, so much massive star explosions, core collapse producing most of the alpha elements, and type 1a supernova making the iron group. But then the big question, of course, for a long time was where you got these heavier elements. In particular, about half of them are produced by some rapid neutron capture, our process. That was known since the 50s, just based on nuclear physics, that you can get the right patterns by neutron capture. But the origin of where those happened has been one of these long-standing open questions in astrophysics. And with kilonova, we're starting to get our first direct evidence of where they might come from. If you read the old textbooks, the idea was that you were getting these heavy elements in core collapse supernova. And that's because the conditions you need to make heavy elements by the SAR process is that you have to have some neutron-rich outflow. And it's parameterized by this YE parameter that's come up a bit, which is really just electron fraction, or really same as a proton fraction, number density of protons over the total number of nucleons. So we want that to be less than a half to make some kind of neutron capture elements. If it's about a half, you prefer to go to elements like nickel 56. So naturally, the idea of making heavy elements has revolved around neutron stars, where you might have high neutron abundances, either the formation of a neutron star in a core collapse supernova, or the merger of two neutron stars, or a neutron star in a black hole. And the main difference, and Svi pointed this out a little bit before, is that this would be a common event, but may make a very low yield of our process, if any. And in fact, the more detailed models that people do of this proto-neutron star and the wind that's blowing off of it may produce our process have found it very difficult to make the right conditions to build up our process. The YE is actually not very much less than 0.5. In fact, sometimes the outflow is a YE that's greater than 0.5, so you're not in very neutron-rich conditions. And you are unlikely, to the best of our knowledge with the simulation so far, to make our process elements, at least the heaviest ones. Maybe you can make some of the lighter R process elements. In fact, I should go back to this the slide before and point out this distinction, just so we clarify. We talked a bit about it already, between sort of a light R process elements and a heavy R process elements that are kind of broken up around barium or so. And we'll see that there's some variation in the stars we see with the abundances in light and heavy R processes, and there's physical reasons to think that there may be distinct conditions producing the two of those. So maybe in a core collapse supernova, you may make some light R processes, some exotic types of supernova, magnetar, jet-powered supernova. Maybe you could make a heavy R process, but that remains to be debated. But with neutron star merger, it seems almost unavoidable to make some R process elements. This is going back to ideas of Latimer and Schramm and others. These would be rare events, but they may make a high yield. But from the point of view of observations, what's really fascinating about this, if this makes any R process, well, we really have very little direct handle on it. There's maybe 10 to the minus 5, 10 to the minus 6 solar masses of our process at the center of this huge cloud of many solar masses of ejecta. you really can't pick it out. Whereas the ejecta from a merger, making the kilonova, is a beautifully pure sample of heavy elements. And we'll see that we've gotten our first chance now to actually probe directly emission from that material. So the real question that you would want to answer if you're thinking in terms of the heavy elements is, how often do each of these events, in particular the neutron star mergers, happen? What's their rate? And how much our-process material do they produce in a typical event? And now we're starting to get handles on both of those, and it should only get better with time. So I'm going to tell you a little bit more in detail about the emission you would see from one of these mergers. The idea is you'll eject some radioactive material and you'll have a supernova-like glow associated with it, not unlike what we talked about with the type 1a supernova that are powered by nickel. The only distinction would be that the kilonova have different materials and radioactivities and would be much dimmer and shorter lived. And we've talked a little bit about these scaling relationships, the luminosity scales with the sort of radioactive heating at peak. If you run through that sort of problem set workshop I sent you, you actually can derive this relationship called Arnett's law, that the luminosity at peak is related to the total radioactive heating. And then we've also seen several times this effective diffusion time through a expanding medium that depends upon mass, opacity, and velocity, which sets the duration. So the fact that the masses ejected in a typical neutron star merger are only a percent or so of a solar mass compared to a type 1a would mean you're getting much dimmer and shorter lived transient, which is why before the recent event there was no really strong independent or blind detection of that. People have gone back in the data and looked for these sort of blips, but they're hard to find with the cadences that we have now.
So then,
okay.
This relation that the luminosity is proportional to the mass of the nickel at the peak.
Yeah.
So the peak is where photons escape from the whole macronova.
Right.
Material, or the whole material, whatever it is, macronova or not.
Roughly, yeah.
What's that?
Yeah.
Okay. Oh, you take at the time of.
At the time of peak is what it usually.
So it's not just the luminosity.
It's a characteristic luminosity, but it does match at peak. And Udi showed, I think, in one of his talks that's just a rough relationship. Sometimes the peak can be off by a factor of a few to the radioactive heating. But in these one-zone models, you can actually derive this relationship. You can derive, an expression for the luminosity and show that when that luminosity is maximum is when heating balances sort of the diffusion losses. People use this Arnett's law all the time. If you're curious where it comes from, it's a few lines of algebra to derive it, and that's laid out in those notes I gave you. I won't go through it here. The other big question, and again, I'm just giving a quick overview, and then I'm going to go into everything in more detail, is what the opacity is here, and we've talked a bit about it, and I talked about some of the radiation transport physics that's behind it, and I'll come back to that. It's really driven by lines here. Again, people have often just taken characteristic values that seem to fit the data, but one thing that's was crucially known, and Svi mentioned this already, so I'll just reiterate it, is that if you have very heavy R process elements, the opacities are quite high. You'll get a longer diffusion time and a broader light curve with the emission mostly coming out in the infrared, whereas if you have lighter R process elements, you get sort of a shorter time scale, maybe something brighter and bluer. And so this was a nice diagnostic here, blue versus red, of whether you have light or heavy R process elements. And I'll explain that in a little bit more detail as we go on. But the situation was, prior to the recent event in 2017, the theory had developed to a certain point of making predictions of what we would see, and the observers were very depressed in general, based on the idea that these events would be sort of very dim relative to supernova, and if they made heavy R process, it would be very red, which is hard to search in, and not to mention that when LIGO detects the source, It usually has not a very great localization, so that you have to search a huge area. This is searches that were done for the original black hole mergers. People searched this very large volume area here that was several hundred square degrees, looking for some sort of transient, even though they didn't really expect to find any. But it was definitely good practice for when the neutron star merger event happened. So from the point of view of, earlier in 2017, I would have said this is an incredibly difficult task to find a kilonova. You're looking for something dim, red, and in a huge volume. And I thought maybe we'd be 5-10 years from now, we would be talking about it in detail. And we got lucky, and the story evolved much more quickly than that. But let me talk about it, though, more from the theorist point of view of how the theoretical ideas developed and what our picture was. And then we'll come back to the actual observations and see how they fit into that picture and where some of the open questions lie. So, for many years, this was really just the product of theorists' imaginations and calculations, trying to simulate what happened in a merger, which is many stages of different calculation, right? With very different codes, and we've talked about a bunch of them throughout this school. There's the binary evolution, how you get to some system where you have some tight binary of neutron stars that will merge on the Hubble time. There's the merger itself, which is taking milliseconds, tens of milliseconds that you need to simulate, which is some multi-physics calculation. You're trying to capture the hydrodynamics, the GR, the equation of state of this nuclear matter, which plays a role in the neutrino physics. I'll mention some of the effects those have. And the merger itself probably ejects some material that can contribute to the kilonova. And then what's left behind is probably some compact remnant with a disk around it, and that's going to evolve on some longer time scale, some viscous time scale for accretion that we also heard about in this conference. And so you want to model on a longer time scale, maybe seconds now, the dynamics of that wind and whether material can get blown off of the disk in that region. And then, assuming some material gets ejected in this merger, you want to think about the nucleosynthesis of how that would build up into heavy elements made by the R process. All that nucleosynthesis of building heavy elements is happening on maybe second time scales. And you may make some very neutron-rich elements that will then radioactively decay, beta decay on time scales of weeks, months, or so on. And that's going to power the kilonova transient we see. And this is where we get into all the radiation transport and the line physics and so on that we discussed. So there's many different aspects of it, and you can imagine there's complicated physics and uncertainties in every step along the way. I'll try to give you a little bit of picture of each, and then get to the observable signatures. So let me just say a little bit. Of course, I'm going to have to go quickly, but through the merger of neutron stars. Again, this is a problem that's been done in many groups for many years. This is one of the original kind of calculations by Stefan Roswag of two neutron stars coming together. And you can see sort of a general property as they merge. Basically, some material is getting just tidally flung out, but most of the mass here is going into this central remnant. And then there may be some mass held up in a capillary and an accretion disk around it, right? So roughly speaking, you look at a simulation like that, some 90% or something is going into the central remnant. Is that wind up being a neutron star or a black hole? That's one of the big questions that everybody's asking, and there's not really a direct answer to it. It depends upon what you think the maximum mass of a neutron star is, which depends upon the equation of state that we don't know in all its detail. It may be able to live as a massive neutron star above that maximum mass for some period of time before losing support and collapsing to a black hole. We'll talk a little bit about that. But there's some massive thing. There's some accretion disk, which I said will accrete on a longer time scales of a second or a few seconds. The merger itself is sort of milliseconds time scale. And then there's probably some small amount of material that gets dynamically ejected. Now this was actually an old Newtonian simulation, or sort of a post-Newtonian. The dynamics look a little different in GR, and you actually can kind of break out three different types of ejecta you get in a typical neutron star merger that have somewhat different properties, right? So you saw in that simulation material just getting tidally flung out. You might call tidal tail material, and you can get something like 10 to the minus 4 to 10 to the minus 2 solar masses or so on. The exact amount will depend upon the masses of the neutron stars and their equation of state. And we can talk a little bit about that. And the velocities flung out will be something of order the escape velocity from this neutron star system. So, 0.2 to 0.3 speed of light. It'll be very neutron rich, so very low YEs. This is basically just taking cold neutron star matter and ripping it off and flinging it out into space. So this is a very promising site for making very heavy R process elements. It'll be cold. It'll be heated up a little bit as nuclear reactions take place, but it'll generally stay cold. But yeah, Ken.
So then when the R process site occurs is during the touch side of the two neutron star, or what exactly the geometry of this R process site in this case?
I'll show you a little bit more about the geometry. So at this stage, this early millisecond phase, you're just flinging out material from the neutron star and its crust and actually digging a little bit even deeper into the crust here. So the composition here, initially it may be somewhat complex. I mean, there may be nuclei inside this neutron star that are very neutron rich and start to drip away once you eject them. But as it heats up, it probably goes to some nuclear statistical equilibrium. And then as it's expanding, it'll start going through the R process. So at this stage, we're not thinking about the R process yet. But that'll come later. What you see in the general relativistic simulation is actually most of the mass is not necessarily getting tidally ripped off. If you have nearly equal mass neutron stars, they kind of sort of collide together. And you get this shocked interface between them, and material gets kind of squeezed out in these polar regions, right? And you can get similar amounts of mass, maybe even more mass coming out in these polar ejecta. Similar velocities, relatively high velocities, but it's much less neutron rich, and I'll talk a bit about that. And that's because this material is hot and shocked, so it'll start radiating neutrinos, and neutrinos will, weak interactions will change the neutron richness of that material. So it'll have also a slightly different geometry and a different neutron richness. And then we call both of these kind of dynamical ejections because they're happening on the millisecond time scale. But after the merger, as this disk evolves, you'll have a wind evolving on a longer time scale. That actually, as material gets blown off these winds, you may actually get more material coming out post-merger compared to in the merger itself. And that material is going to be moving at somewhat slower velocities because now you're talking about an escape velocity from a disk that's more extended than the neutron star system itself. So you expect to have lower velocities and maybe some range of electron fractions. So we'll see that. So we have these different components that were identified in simulations. Let me show you some plots. This is a nice simulation by David Radice showing the dynamical ejecta. So this is sort of what's coming out in this process of the merger itself. And you can see kind of what I was describing here. There's density on this side and then an electron fraction here. So along the equator, you're sort of flinging out this cold neutron star material that's very neutron rich. As blue is very neutron rich. Actually, you should have done the color. You should have done the color scheme reverse because we'll see that this emission will be mostly red, and this emission will be blue. But he colored it blue, and so that's sort of the tidally disrupted material. And then along the poles, you get this sort of squeezed material. And that material is shocked and it's getting irradiated by neutrinos. So you have neutrino heating and cooling here. And that raises the YE here. Now it's kind of in this red region, something of 0.3, 0.4 or something. There'll be some range, right? Okay. Why is the YE higher? Well, you have neutrinos being generated here, say, by pair processes. So you have this stuff getting neutrino irradiated. You can have these sort of weak interactions happening, right? Captures onto neutrons, changing neutrons to protons or protons back to neutrons and so on. And in general here, the irradiation coming from these deepest regions, you're getting roughly equal numbers of neutrinos and antineutrinos coming out, okay? So the natural result is to sort of drive you to something closer to symmetry, to YE of 0.5, if you're strongly radiating by these neutrinos or antineutrinos. So capturing that neutrino physics is actually one of the crucial things for understanding the composition that comes out as a result, the kilonova signature we see. And it's one of the aspects that the simulations are really, well, it's at the state of the art of the simulations, actually. Different groups doing this with different schemes for doing the neutrino transport sometimes get somewhat different results. And no one's done the neutrino transport in its full generality. There's usually some approximation that's gone in that may compromise the results. But this seems to be pretty, I would say, most of the simulations, pretty generic, that you get sort of higher YE material along the poles and lower YE along the equator. Okay? And then there's systematics that will depend upon, you know, what the system is, what the equation of state is as well. And so there's several different papers that have looked at this. This is a set of simulations that was done with, this is actually SPH with some conformally flat treatment of GR, but it just gives a nice description of what kind of masses of ejecta you would get and how it depends upon different processes. In particular here, it's showing you what the dependence is on the equation of state of the neutron star, in a sense. Okay, so that's one of the big unknowns, is what the equation of state is. If you specify the equation of state of a neutron star, then for some mass you'll get a radius here. And so they've used radius here as sort of a proxy for the equation of state. But each point here is a different simulation they did with a different equation of state, and the details of the equation of state. You know, they may have the same radius, but slightly different equation of state properties. But you can see some interesting systematics here. This is a symmetric merger. As the equation of state gets softer, so you have more compact neutron stars, you see you get a larger amount of ejecta mass, maybe going up to 0.1. And most of this ejecta, in this case, is this squeezed ejecta that you saw coming out in the poles as they come together. And the explanation here is that as you have a more compact neutron star, well, this collision happens sort of closer together, deeper in, where the energy scales are higher. So you have a sort of a more violent collision that will squeeze out more matter, as opposed to here, where you have a sort of softer collision, and you'll get less matter squeezed out along the poles, right? So that's a trend, at least seen in these simulations. And of course, other groups are working on this. And here's something showing this is now an asymmetric merger. And generally with asymmetric mergers, different mass ratios, you can get maybe slightly different amounts of mass, maybe a little higher mass, given that you can, in a sense, you'll get more tidal ejecta often in these cases, since you can tidally disrupt the larger neutron star more easily. So there's some variation, and people debate this all the time. How much mass can you eject? It's often, you know, going up to about 1% or so in a lot of these simulations, and different groups get different values to a factor of a few. But it's usually around 1%, which we'll see maybe a little bit in tension with what we infer from the observations, but not so much that we need to worry too much. That was the dynamical ejecta. There'll be ejecta that happens after the merger, once we have this disk and it viscously evolves, and there's been work done on that as well. A lot of the original work done by Rodrigo Fernandez. These are now just 2D disk simulations. We heard about accretion, and in fact, the actual physics is going on in 3D, really driven by MRI turbulence here that's going to drive the viscous evolution. Here it's just using a sort of artificial viscosity, an alpha viscosity, to follow the evolution. But basically what's going to happen is over time, over a viscous time of about a second or a few seconds, this material, some of it's going to accrete into the black hole, but you also unbind some material, and it flies out, right? Okay. And the unbinding is become because this is hot. It's radiating neutrinos, so neutrinos can actually blow material off. There's some component of neutrino-driven wind, but a lot of it is just viscous heating. You know, the viscosity is heating the material and unbinding some small fraction of it at the expense of material going in. Okay, and you can wind up ejecting a good fraction of this disk, making a pretty large ejection here. Questions? Again, the neutrino irradiation in this disk phase is crucial for determining the composition and at the end of the day, what we're going to see. So, material that's in the disk and getting flung out of the disk is getting radiated from neutrinos from these dense hot regions. And if the material if the remnant at the center is a neutron star, well, you have a hot proto-neutron star that's going to be radiating a huge amount of neutrinos, not unlike what you get in a core collapse supernova. Some large fraction of this binding energy is going to be radiated in neutrinos as long as that neutron star can survive and not collapse to a black hole. And so again, you have weak interactions driving it. So this is just a calculation of the neutrino transport showing you sort of the mean neutrino energies of tens of MeV, radiating largely the polar regions and so on. Okay, so that effect of the neutrino irradiation tends to also drive up the YE of this wind. Okay, and so here's sort of the final outcome of one of those 2D disk simulations, showing the ejecta here, which actually looks, fairly spherical at the end of the day. In the disk phase, it may preferentially come out in the polar directions, but it tends to sort of be hot and expand, and over time sort of take on a more spherical geometry. And in the outer regions, which were heavily irradiated with the neutron star neutrinos, you're getting YEs of sort of 0.3, 0.4 or so. The interior tends to be a little less neutron rich because the neutrino luminosity is dropped. So this later ejected material is not as neutron rich, and maybe the neutron star may collapse to a black hole at some point. So we may get some sort of layered structure there as well. And in fact, this is showing you the results a little bit more quantitatively of what kind of material will get ejected in this post-merger phase from the disk. And it's quite sensitive to the central remnant, whether it collapses immediately to a black hole or whether it survives some period of time as a neutron star and then collapses to a black hole, or maybe it could survive indefinitely as a neutron star. And here is just showing you histograms of the different YEs you get from the different disk winds, right? And so work with Brian Metzger and Rodrigo Fernandez. Here's the tidal tail ejecta, which we said, just ripping off material from a neutron star is very neutron rich. These disk winds tend to be less neutron rich because they're being neutrino irradiated. But you see two important trends here that will be of relevance to try to maybe infer something about what the central remnant was in the recent neutron star merger event. That is, if you had prompt collapse to a black hole, you don't get much ejected mass in the disk, and it tends to be quite neutron rich. As you increase the lifetime of the neutron star, you shift things to higher YE, and you also get more mass ejected. Why do you get more mass ejected as you increase the lifetime of the neutron star? Relatively simple answer to that. What's different between a neutron star and a black hole? The neutron star has a surface. So if you have a black hole, most of the material can get just ejected into the black hole. But if you have a neutron star that lasts forever, well, there's some hard surface there, and eventually all the disk material is going to be ejected. And so you'll get just about all the disk material. So the fraction of the disk that gets ejected will be some function of the lifetime of the neutron star. And so based upon the properties of the ejecta, one can try to say something maybe about how long the neutron star, or hypermassive neutron star lasted as well. So you eject this material, it's at certain YE, and then as it's outflowing and decompressing from these high densities, that's where the nucleosynthesis takes place, and you build up the heavy elements by the R process. And Svi went into it. I won't say much about it other than to kind of describe that there's different pathways that you'll take depending upon how neutron rich you are. So if you had this, say, dynamical ejecta that was very neutron rich, well, you have a lot of neutrons around and you can sort of build up to the heaviest elements. So this is the chart of the nuclei. These are the stable nuclei here. And here you follow some pathway that's actually quite close to the neutron drip line. Okay. And I should say, experimentally, we don't know very much about the nuclei that are this far away from stability. We know somewhere in here, and people try to extrapolate out into these regions to do these calculations. But that's one of the uncertainties that people are pushing on with experiments to try to learn more about these very neutron-rich isotopes. Okay. If you have a less neutron-rich ejecta, so this might be YE of 0.1, maybe this is YE of 0.3. Well, you get a pathway here. It's hugging stability more closely, and actually, it only gets up to a certain point where you sort of run out of neutrons and the flow stops. Right? And there's some physics here. There's this is a closed shell nuclei here, so this is a particularly stable nuclei, long beta decay lifetime. So the flows tend to hang up at these stable closed shell nuclei, magic numbers. And so if you have a high YE, you tend to sort of make it to this point and not cross over. Right? You either sort of make it over this barrier or you don't. Right? And these are going to produce the peaks in the abundances. And so here's just some reaction network calculations I've done for different values of YE, so you can see what you get. So for low YEs, right, you tend to build up to the heaviest elements. And get these peaks here. There's mostly everything, this is a black line, mostly everything above atomic number of 40-something. Same as Y at 0.2, it's actually pretty robust because you have so many neutrons that you kind of build up to the heaviest elements and sort of fission back and cycle around until you reach some robust pattern. And once you drop below YE of about 0.25 or so, you get stuck. You basically get stuck at this closed shell, and you don't make it up to the heaviest elements. So you only make light R process elements as you go along. Okay. So there's sort of this magic number that people quote a lot of YE of about 0.25, that if you're above, this is sort of the mass fraction of heavy elements, in particular lanthanides, which I'll mention are particularly important for the opacity and what we see in the kilonova. And so for this blue line, this is the mass fraction of lanthanide. So if you're quite neutron rich, you'll make about 10% of your ejecta will be lanthanides or actinides, so the rest will be other heavy elements. And there's a very sharp transition here. If you're above that, you don't make it. So it's sort of, it's almost an all or nothing. Either you make it past that closed shell or you don't. It's not quite so simple. This question came up of, well, what does the temperature or density matter also for the elements you make? And as I said, that's often parameterized by the entropy or entropy per baryon, which is it's basically a temperature cubed over rho. And so what that entropy is, it's usually in the range of 20, 30 in these outflows. That transition point may shift somewhere between 0.2 and 0.3 or so. But in a sense, there's some cutoff in this region. If you're below that, you're heavy elements. If you're above it, you're not. Okay? And so you make some elements here, and you can compare it to solar system abundances here. So if you just had very heavy, just very neutron-rich material, you get something like this bluish line that's just matching the heaviest elements. You get these peaks here, which are associated with those magic number stable nuclei where things pile up. But if you want to make both the lighter elements and the heavy elements, you need a composition that includes both, say, very neutron-rich dynamical ejecta and then some less neutron-rich either wind or some other material. And you put those in the right combination, and you may be able to match all these peaks. Okay. So to put it together, this is just a schematic, illustration of what we think might come out of a generic neutron star merger, right? There's these tidal tails, material that got stripped off that's quite neutron rich. There's this shocked polar material that comes out from the collision itself. And then there may be this disk wind coming from the central material that's moving somewhat slower but may have somewhat mass. And so that's sort of the generic kind of theoretical picture that we had in our heads for some time. different components all within the same system, but different composition, heavy, light. And the wind may depend upon whether this is a longer-lived neutron star or a shorter-lived neutron star. Any questions on this? Yeah.
So the disk wind is sort of always advertised as a way of telling whether it's a neutron star or black hole. But it's clear that you need it at all to do everything with shock ejector plus tidal tails.
Yeah, I'll talk a little bit about that. I mean, it depends on how how much detail you want to go in towards your analysis. So we'll see with the, I'll get to the kilonova, you can try to infer something about the mass and velocity of material that is ejected. And the estimates were made, they're made, suggest that there's a rather large mass ejected, maybe 0.05 solar masses, which would really push what you could produce in these dynamical things, but maybe easier to do in a wind. And there's also some indication in the spectra that there's some material moving at sort of lowest velocities, 0.1 c. Which would be more natural for a wind. So you can try to, it's still early stages, I think, for getting too deep into the interpretation, but you can try to tease out what the components are based on the observation. So I'll show that.
Then when you have a shock pore, will you create something like a jet structure?
Well, this stuff is not a jet per se. It's just material that gets squeezed out at non-relativistic velocities. But you're right. There's also, say an engine here that we think probably produced some jet and some cocoon that maybe moved up in this direction. And so that actually may reshape this material in this that was just ejected. Originally, it may heat it. Maybe it changes its composition. People are starting to look at that. That's a good question to look at. What's the, how does the jet interact with all this? But in this picture, we haven't turned on a jet yet. Okay. Is it what?
Is it clear that the tidal tails are unbound?
Yeah, in the simulation, some material of the tidal tails is unbound. I mean, there's some range, right? So it's kind of what we talked about in tidal disruption. Some unbound material, but then there's some material that's bound and will fall back. And
it's not exactly like tidal disruption, because in tidal disruption you start with an object that has zero energy.
Yeah.
Here you start with an object that has a very negative energy.
Yeah. And it's You're already very negative energy, and you have sort of more equal mass systems. But there is some range of binding energy, I guess, where energy of this ejecta. So some is unbound at these velocities, and some material is falling back. And so there have been some studies of how that fallback material would interact with the disk wind that would blow it out. And so some of that fallback material may become unbound as the disk wind pushes it out or something. But there's some interesting dynamics going on in the interplay there as well that one can look at. Yeah. Yeah, in general, if you have a stiffer equation, say a larger neutron star, then it's probably easier to disrupt it and get more tidal ejecta. And I'll show you if you have a more asymmetric system, so say a black hole with a high mass and a neutron star, it's going to be easier to disrupt that neutron star and get more tidal ejecta. Yeah.
Will the tidal tail and the polar ejecta eventually also become isotropic, or are the
No, these basically stay in this geometry, so they kind of flung out equatorially, and then everything at this point that I'm showing you is sort of in homologous expansion at this phase. So everything, this geometry basically stays frozen in, and the whole thing is expanding. Since it's cold material, there's no reason really for it to sort of try to close in on itself. I mean, there is some radioactive heating that sort of puffs it up a little bit from what you would get if you just ejected pure cold material, but it never really becomes spherical, at least in the simulations. Okay, what do we see, though? So this is the ejecta. So we see a kilonova. Going back, Liam Paczynski first suggested that you might have something like that, and Metzger and Roberts did a more careful calculation, but you have some radioactive cloud. Okay, this is not a kilonova. This is some supernova remnant that I found a picture of, but okay. It's originally very dense and small, but it grows, it's moving at, some fraction of c. So at a day, it's already, this is wrong. It's not an AU. It's about 100 AU, the size of the solar system, right? It's quite large. And the densities have dropped to something quite low, from neutron star densities to something that's really quite tenuous here. And then it's being radioactive heating. So again, if we look at our toy models and the analytics we've done for light curves, if you just took this, this hot material that got ejected but let it expand, well, all the energy would just go to adiabatic expansion and turn into kinetic energy. You wouldn't see anything if there was no radioactivity to heat it back up. So most of it's sort of beta decay. You may have some fission if there's heavy elements or alpha decay happening. There's been some speculation that the fastest material may actually freeze out with some free neutrons that could decay on timescales of half an hour or so, producing sort of an early bump in the light curve. But that's basically what we're seeing from a kilonova, this radioactively heated cloud at temperatures, which again, you could estimate by these analytics, but the luminosity is something like 10 million solar luminosities. The temperatures are like 5,000. This is all radioactive heating. So you've heard some of this already, that the heating tends to follow some sort of power law, like T to the minus 1, or more accurately, T to the minus 1.3, which we heard was due to the fact that you make a whole range of different isotopes with different half-lives. And this is some calculation by Stefan Rosbach showing that these are different values of YE, so different compositions. Some are heavier, some are lighter elements. They all kind of produce the same sort of heating rate, so it's fairly robust. Well, it depends on how much you care, right? I mean, look how this is a very big dynamic range, right? So there's variations of factors of several in the different heating rates. And actually, this is, again, dependent upon properties of nuclei that we don't know all that well. So if people use different nuclear inputs, different nuclear mass models, sometimes there's factors of 5 or 10 in the heating rate. So actually, how much radioactive heating is one of these things that we need to know better. It used to be fine to be off by a factor of several, but now that there's real data from a kilonova, we'd like to know it better. And actually, you can see if you go too high in YE, you have actually not, the heating is drastically different. And actually here at 0.4, you're only making a few radioactive isotopes. You can kind of see them. There's some some dominant half-life here and some dominant here. Yeah. So actually, we can rule out that the YE was too high, or else we would have never been able to power the kilonova we saw. Seems to be somewhere in this range. But the heating rate itself is hard to distinguish between how neutron-rich you were. Okay?
Why is there such a big jump between everything and 0.4?
Well, I think it's just the different nuclear, how far you get, right? So again, there's these different jumps in the peak. So at YE 0.4, you're sort of only making a narrow range of elements here that have maybe a few long-lived isotopes, whereas the heavy elements, you're making some broad range of elements with all different sorts of half-lives. But it just comes out of the nuclear physics. I don't know, maybe there's a deeper understanding of why it jumps like that. I got to go through this all again. And we can get into the details of the radioactivity, but basically most of it's coming out in beta decays. This is some fraction showing you beta decay energy. And the beta decay energy is coming out as gamma rays and electrons and so on. Some of it can come out in alpha decay. And this is, again, showing you different nuclear physics models. And they predict something different in terms of how things decay and how much energy you get. But another key factor in all of this light curves is it doesn't matter how much radioactivity you make. It matters how much of that radioactivity gets absorbed and heats the ejecta to be radiated, so how effective that thermalization is. And so this is work by Jennifer Barnes, calculating how much of the radioactivity actually gets absorbed in the kilonova debris to heat it. And you can see here, so the gamma rays that are produced from beta decay, actually those escape quite easily, quite quickly. After a couple days, most of the gamma rays are just gone. You lose a lot of energy that way. You lose the neutrino energy as well. The betas can thermalize with some efficiency of a few tenths of a percent. Similarly with alpha. So of all the radioactive energy, especially at late times, we may be only tapping into 10% of that or so in terms of powering the kilonova. And so understanding this physics, this is sort of state of the art in terms of understanding it, but again, it depends upon a lot of the nuclear physics that we're still working out. But basically, you want to predict what you're going to see. So now you're doing a radiation transport calculation. You can do it with Monte Carlo particles flying out of some cloud. And it's doing the physics that I've talked about in the other lectures. These clouds, these photons are Doppler shifting in the co-moving frame. They're going from line to line and scattering around and doing all that fancy stuff, right? And they're feeling the opacities, as we talked about. This, again, was for solar composition. Electron scattering is important, but there were all these lines that blended together, and we talked a bit about how those lines form sort of a, there's enough of them, form a pseudo-continuum opacity as you step from line to line. There's a lot of lines, so here's a more, detailed structure showing you over some range, all the different lines that are coming in here. There's actually too many lines to, in most calculations, try to resolve all these lines. We talked about how narrow each one of these lines are, right? So we're usually going to do some average. That's nice. So if I look, for example, at this little slice of wavelength space right here, and I zoom in, this is sort of what the opacity actually looks like. So there's just tons and tons of lines, and we're expecting the photons going through, just like we talked about. They'll then hit this line and hit this line and so on. So hard to resolve that in a real calculation, so we're going to do some sort of averaging of that. How many lines there are? Yes. Yeah, so you can count. For this conditions, right, how many of these lines are right? This is over 20. Yeah. Of course, it depends. I'll show. It depends on what wavelengths you sort of get more lines going in here as well. But we have. I'll tell you about these. We have lists of these that we can do. And here's the physics that I don't have to go through because I already talked about it. But the photon moving through is redshifting, hitting line, hitting the next line. So the mean free path, again, doesn't depend on how strong these lines are. It's really the spacing between these lines. And so the averaging technique we do is what I derived last time. Just sort of count the spacing of strong lines using the Sobolev method, and there we go. So this is Rim's question, how many lines are there? Well, it depends upon which elements you're talking about. Some elements have lots of lines, some elements have a few lines, and actually that comes down to some basic atomic physics of where you lie on the periodic table, so just your regular quantum mechanics. If you have elements that have their valence electrons in the S shell, well, there's not many ways to put electrons into an S shell. You have sort of spin up and spin down. So not a lot of configurations of different levels and transitions between levels you have there. But if you're in the P shell, this is the L equals 1 orbital angular momentum. This is somewhat more complicated. The D shell is even more complicated because you have an L equals 2. I'll give you the numbers in a second. So iron sits right here in the middle of the D shell, so it's one of the most complicated species that we have in astrophysics. That's why it's sort of the most important species in astrophysics, most astrophysics, because it's sitting right here in the D shell and it's relatively abundant. But in these kilonovae, we have very weird compositions that are mostly heavy elements or largely heavy elements that may include these lanthanides and maybe even the actinides, which are a heavier version here. And these have the F shell valence electrons and are correspondingly more complex, right? So I did the numbers here. You can do this calculation, of course. In detail, it's a mess, but in broad sense, it's simple quantum mechanics, right? If I have electrons in some orbital with quantum number L, well, the degeneracy there is just 2L plus 1 times 2 for the spin. And if I say if I put n electrons in one of these L orbital angular momentums, how many different configurations can I put in to just choose n different electrons to put it in g different spaces right here. So this standard binomial thing. So, and then you can see the results here. So the S shell, the hydrogens and their analogs, well, only 2 spaces, not many levels, not many lines. The lines will be sort of the number of levels squared, the number of different ways you can go from line to line. And then if you go to the P shell, well, okay, now this combinatorics is something like 20. D shell, now we're talking about something like iron. If I put, fill iron halfway through, now I have something like hundreds of levels and many lines. And then the F shell, these lanthanides, you see this number. So these factorials grow quite impressively. A factor of what's this, a factor of 10 or so in the number of levels, factor of 10 squared or 100 more lines. And this is not a robust calculation because there's different sort of electron configurations you can have. But it's a rough counting of how many levels they are, and all those levels will be split by quantum mechanical effects, so orbit-orbit interactions, spin-orbit, and so on, stuff you learn. And so, but just by rough counting, there's a factor of 10 here and maybe a factor of 100 in lines. And what we talked about with the opacity, right, it was sort of what matters for the opacity is the number of lines, right? You go from line to line, not so much how strong those lines are. So just from this counting argument, you could say lanthanides should maybe have, they have 100 times or so more lines, they should have 100 times more opacity. This is just another way of plotting the same thing, showing sort of that binomial combinatorics for each of these elements, right? So as you fill a shell, it's not very complicated because you can't configure it, but as you get half filled, you start to have the most number of permutations. And so you have this pattern of filling these things up, and then here's the lanthanides here, right? And here's these, and then the middle of it is gadolinium, which is the scariest of all lanthanides, the most complicated element on the periodic table, right? So what do we do? Oh, this is just to show you how painful it is. I mean, these are, we don't have all the data, but we have to somehow try to estimate these number of lines. So there's not a lot of experimental data, but you can do some atomic structure calculation. It's just a many-body quantum mechanics problem, but it was the kind of thing that was very exciting in the 1930s, and then people got bored of it and did other atomic physics. But now it's kind of interesting again, because we want to know in particular how many lines there really are and how many levels there are and what their level distribution is like. And so here's some calculations we did with one of these codes. These are just showing you all the different configurations of different elements that we explored, how many levels and lines we get. If you're interested, again, the atomic data, you run one of these atomic structure models, you can put in all the conditions, but they're still approximate calculations. They're not really, surprisingly, you can't just solve the many-body quantum mechanics problem perfectly. You have to make some approximations and tune some parameters. And that means that if you look at the energy levels that you get out, so for some of these are measured. So this is neodymium, which is a lanthanide, and these stars are actually measured energy levels, the ground state, and the first few excited states are the excited states of the different configurations. If you run a model just kind of blindly, you get something like these blue things, which is not so bad, but it's not exactly the right atomic structure, right? So the lines that you predict are not going to have the right wavelengths. You can tune the model to this red, do a little better or something like that. But this is what's done, basically. People, run an atomic structure model. They tune it until they kind of fit this experimental data. And if it fits it, they say, OK, well, calibrated my model. Now I can calculate all the line transitions and hopefully get the right answer. But we're not at that stage yet. There's still more work needed to be done to calibrate these for all these different complicated species that we don't have a lot of information about. But the nice thing is there's so many levels here and so many transitions that to get the rough idea, you don't need to know exactly all the level energies. You just have to kind of get it statistically correct, and things will look pretty robust. And so here's what the atomic energies levels look like. This is hydrogen, which you know well. S shell, here's silicon, a P shell, so it's a little bit more complicated. And then iron is quite a bit more complicated. It's a D shell, so this is what people working on type 1a supernova go crazy about, trying to model all these lines in, between all these levels. And then here is a lanthanide where, I can even resolve those number of lines. So it's a very opaque material, even the level structure is opaque. And so the opacities you generate from that, and the opacities are basically, we kind of know how to calculate them in principle, right? You kind of see how many of these levels are populated. This line here is sort of the thermal energy level. So remember, in this expression, everything sort of had this e to the minus delta E over kT. So these are the levels that are generally populated, and you can calculate all those transitions. And so We get factors of maybe 10 or 100 higher opacity in general for these lanthanides. Some bumps here that are associated with changes in ionization state. And then sort of a drop-off when things start to recombine at temperatures of around 2000. This is showing you, just this another opacity as a function of wavelength. Again, this is all these lines that sort of blend together into a pseudo-continuum. There may be a few lines that are particularly strong, and they may make an absorption feature in the spectrum, like we talked about on top of the continuum. But you can see the continuum is not a flat, it rises generally to the blue because there's more transitions at bluer wavelengths. But much higher opacity, especially in the infrared. But the periodic table, is good. I mean, here's iron, here's osmium, very different weights, but they lie on the same column of the periodic table. And so they have actually quite similar opacities, right? In detail, their structure is different, but statistically, they're quite similar. So we can have a pretty good handle, here's two, just kind of in a statistical sense of what the general opacity is. If we want to know where all the individual bumps and lines are, we need to know the structure in detail. But if we just care about the general opacity level, we have some handle on that.
So
Yeah.
I think, would be try to ask this yesterday, but
Mhm.
shouldn't this opacity depend on the expansion velocity?
It doesn't depend directly on the expansion velocities. I mean, it's just a local quantity that depends upon the sort of gradient in velocity, so that dVdr, which is T in homologous expansion. I mean, it does depend upon the density, which is changing with time as well.
But
So,
the number of lines
but-
you cross, if you want to translate it to real distance,
Yeah, so we wrote that down, right? So that distance was just a function of, the spacing between the lines, delta lambda times CT.
yeah, so you got the time there.
Right, yeah. So the velocity gradient is always the same in homologous expansion. dVdr is always the time.
This is function of
So,
time.
yeah, so what matters is the gradient. Yeah, it changes with time and density,
Okay.
but velocity doesn't matter for homologous flows. Yeah. And so that's all taken into account in our calculations. We're calculating this at each point for different temperatures and different compositions and densities. But this is just showing you some characteristic conditions. Maybe I'll skip over this. There was some debate about how to, whether the opacity was much higher by factors of 100 in some of these papers, which I think you can understand now if you want. But since I'm running a little short on time, I'll skip over those details. Now, there's a really cool, maybe fortuitous connection between different fields of physics, atomic physics and nuclear physics. And we just said these lanthanides tend to be very opaque due to their atomic physics structure. And we also said that because of nuclear physics, because of this closed nuclear shell, that if you're below YE of 0.25, you kind of cut off before you get to the heavy R process and light R process. Kind of a funny thing that the lanthanides lie in the region of heavy R process exactly, and the light R process. So so there's a link now between the nuclear physics. Whether you make heavy R process, you'll have high opacities. If you light R process, you'll have lower opacities because you'll lack these lanthanides. I don't think it had to turn out to be that way, but nuclear physics and atomic physics went hand in hand that way. And so here's what happens is you change now the composition of the material that you're ejecting in the kilonova. And here I just did sort of, these are kind of toy models, 1D models with the real radiation transport, but you could do something similar with one of your analytic models. But I varied the abundance of lanthanides from 10%, which is something you'd get from, say, a very neutron-rich flow, to something quite a bit lower. That would be some less neutron-rich. And you see the general trend that we should hopefully understand now. Higher opacity because of these lanthanides, longer diffusion time. Higher opacities, you blanket the bluer bands, you push your photosphere out to larger radii where it's cooler, you get redder emission. A very nice diagnostic here. The color is linking us to the lanthanide abundance. This mapping, of course, is folding in all that complicated atomic physics, all those lines and everything that we still have uncertainties about. But the general trend is somewhat robust. So I think this was mentioned before. There was one case in 2013 where they followed up a short GRB. This is before LIGO was doing anything. And they said, well, if this GRB was a neutron star merger, maybe there'll be a kilonova afterglow. And they looked in the optical. They didn't see anything new. But in the infrared, they did see some glow. And they got a data point here, some infrared excess that you can match. So they observed like a week after the GRB, and they found some kilonova. You could match to a kilonova model with about 0.05 solar masses of ejecta. Right? So this again goes back to what we said. The brightness is a link to how much mass we have, since the luminosity at peak is related to the radioactivity. So this was somewhat, intriguing at the time, but one data point, you're not sure what's going on. There were other GRBs that were observed that had limits or some maybe marginal detection at this level. There's some hints of kilonova. My great hope after this was they would find a neutron star merger and maybe get maybe at 3 or 4 points along here so we could see it rise and fall. Turned out we did much better. Asymmetry, like we said, material may be asymmetrically distributed, and you may get some range in brightness depending upon the viewing angle, which will affect the mass you infer. So if you think that this is more sort of in the equatorial plane, well, there may be a factor of 2 change in brightness. May change your mass estimates by a factor of 2 or so. And so those kind of effects are lying around.
Okay.
Yeah.
So in your in the plots where you showed the amount of element produced as a function of
Mm-hmm.
YE, it looked like for all compositions there was a sharp cutoff at atomic number of 85 or so. So where are the heavier elements produced?
Yeah, I think the models I showed you maybe didn't go out to the, I might have cut off the plot, or at least it didn't go out to the heaviest elements. But you can make even heavier elements if you're neutron rich enough. So you can make it all the way out to Z of 100 or something, uranium and even heavier elements. And a lot of those will decay away quickly, except for the longer-lived isotopes like uranium. But I did confirm that you do make, if you have low enough YE, you do make berkelium and californium. So we're good with that. Those probably were made maybe in these tidal tails. So here's again just the general picture of what we might see in a 2-component model. If you had some blue emission, say a wind and a tidal tail, well, even before this event, we explored that possibility where you had, say, different events, maybe event made mostly low YE, so mostly tidal tail, then you would get something mostly in the infrared. If, on the other hand, you had made mostly high YE material, you would get mostly blue emission. So the idea is going back to this 2015, you might get some blue component and red component, and the relative strength of those 2 components would tell you about how much light versus heavy elements you are. So the theory had reached a pretty developed state. There was predictions of what the spectra would look like. And generically, well, this is for heavy material. Moving at 0.1 C, you see sort of broadish wiggles here. Again, it's kind of like we discussed, although now it's not just one line. There's this whole forest of lines blending together. So these dips are not necessarily associated with any one transition, but they're associated with maybe blends of lots of different transitions. And you may get 2 components in the spectra, kind of 2 peaks, one from a blue emission, one from a red emission. And also this kind of effect, we also talked about with 2Ps that there was sort of a regulating temperature around 2000 Kelvin where things started to recombine and the opacity dropped. So the photosphere tended to fit here. Udi showed that for type 2Ps, the temperature kind of flattened out at 6,000 Kelvin or 5,000 Kelvin, the recombination temperature of hydrogen. The lanthanides recombine at a lower temperature. So there were a number of kind of detailed predictions of what was going on. I can just go through, well, this is just summarizing what I said. You may have 2 sort of components. One's heavier R process producing a red kilonova, another blue kilonova, and there's some, as complicated as the whole process is, it's grounded in some pretty easy or robust physics here about the atomic physics of the lanthanides and the nuclear physics of the flows. So then, well, we didn't expect to see anything for another 5 or 10 years, but then well, you all know they found something. And amazingly, these were the error boxes, error bananas that they had previously with Virgo turned on, and then this neutron star merger happened. It was actually quite well constrained, even without the GRB. So the observers quickly went through. I won't tell you all the exciting stories of how they found something. Here's what the gravitational waves indicated in terms of what the masses of the systems are. Right? We heard about this. Chirp mass, which is constrained quite well, the combination of the two masses, it's harder to disentangle the mass of each element, each component. But they're somewhere in the range of 1 to 2 solar masses. So now this is a neutron star merger. I should say there's really nothing in the gravitational waveform that tells you these are neutron stars. Just tell you their masses are in this range, which you expect to be a neutron star. But there could have been a black hole if there was a way to make a black hole like that, or some quark star or some crazy thing, right? The gravitational waves don't tell you that. It's really the kilonova emission that does. And then, of course, they saw something. Here's the first optical image of the optical counterpart, this little blue glow. A lot of people observed it. Okay, turning redder.
I think at least in principle, the gravitational waves at the very end, maybe they're a little bit out of the LIGO band. So the very end should give you a hint if it's black holes or neutron stars, because you'll see when they merge and the signal stops.
Yeah, I could show you a plot. So when the neutron stars merge, it's a little bit out of bands. It's more sort of kilohertz frequencies, and then a lot of cool stuff happens as they complicated merge together, and you might have oscillations of the merged remnant that may tell you something about the equation of state. But fortunately, that's all happening outside the bands that they can detect. They can detect some constraint on the radius of these events. I think that was discussed. If not, we can talk about it. But right. So you can see some of the tidal distortion, or at least put some constraints on the radii. So unfortunately, it's a little out of the band to see all the interesting merging physics. If we can get an even nearer event, which was maybe unlikely, we would see it, or if they can increase their sensitivity at those higher frequencies. Or if you can co-add a lot of neutron star merger data, maybe you start getting some handle directly. So what did they see? This is what, I'll just show you a little bit of the data. This is optical and infrared data. It was actually quite bright in blue at the early times. Some people say that was unexpected. I wouldn't say it's totally unexpected. I showed you models before where we predicted there could be a blue and a red component. Although this was, rather on the bright end of those, even brighter than the models I showed you before. And there was a red emission too, but it started out kind of blue. And then it faded very rapidly in the blue bands, but started to rise in the infrared. Right? So blue just sort of died away. And the infrared kind of survived, right? So this is now 5 days. It's kind of reminiscent of some of those models I showed you where you might get some longer diffusion time red component and some rapid faded blue component, right? So that's what you see. And again, I had hoped to see maybe they get a couple of those photometric points to look for a kilonova. But it was more of a dream come true, maybe a nightmare, because they got so much data that all of a sudden, all our kind of rough models are put to a very stringent test. But they got spectral series of this event sort of almost every day, starting at half a day after merger. And you can see several things in this series of spectra, right? First is, well, you see this very rapid evolution to the red, right? Started out very blue, got very red. The emission is sort of thermalish, kind of black body-ish. Certainly doesn't look like a, afterglow emission, power law sort of emission. So indication that we're seeing thermal emission like you expect for a kilonova, not some kind of relativistic flow. In the optical, it was essentially featureless. You'll see in the infrared, it was more bumpy. There's some interesting things here, right? Looks like there might be a kind of 2 peaks here, double peak here. So maybe 2 components to the spectrum. Right? And so we can compare those to some expectations from models, some simulations of the light curve. These are calculations of spectra, again, just 1D models where we just controlled changing the velocity from something that you'd expect for supernovas-like velocities, 0.03 c, to something higher. And so we light our process, heavy our process. And the basic idea is if you have lower velocities like a supernova, you expect to see some, absorption features like you do in supernova. But as you go to higher velocities, all those get broadened out until you're at 0.3 c or so. Sort of becomes featureless. All the lines blend together, and that's actually similar to what was seen in the optical mostly. So the indication spectroscopically is that early optical emission is material moving sort of 0.2, 0.3 c from the spectral features. That's consistent with what you get if you do sort of a black body kind of calculation. You say, well, if I measure the temperature of the observations and the luminosity and I infer radius from the black body, you infer that the material had to be moving at something about that velocity. So that's a pretty good indication of kilonova that we're evidence for the velocities we expect for ejected material, and particularly the dynamically ejected material, which reaches like 0.3 c, as opposed to the disk winds, which are more like 0.1 c. So in the infrared at 0.1 c, you kind of would expect to see some wiggles in the spectrum, 0.1 or 0.2 c. Here's some spectra showing some, it's a little much to see, but showing some comparison of these first 8 days of spectra in the optical to some models. And what you see here is, over here, if I do what was Ben called a blue dynamical model, this is material low opacity, so lighter our process. Well, it does a roughly decent job of getting the shape of this spectrum right. Not great, and there's some discrepancy, especially as you go to later times. If I do a material made of red, so this is heavy R process material with high opacities, well, it's not nearly blue enough at early times, but at later times starts matching up. So the indication spectroscopically, you can argue, is for two components. At the early time was from some blue ejecta, lighter ejecta, and at later times we're seeing a component of heavy material with red ejecta. This wind model, I think, was published before the event, which had sort of two components, which kind of does what you see. So the data was insanely good that they got. This is, every day or so after the event, all the way from optical to near infrared. Seeing here the emission, and actually now you're starting to see wiggles in the spectrum in the infrared, which was fantastic. That's sort of the smoking gun here of some supernova-like or kilonova-like event. We're seeing actually absorptions like we expect in supernova. We see the one of this peak in blue kind of dying away and a peak in the red infrared starting to rise. So some hint here as well that we have two components of ejecta. It's maybe a blue component and a red component. And that's sort of the kind of nominal model we put together to try to explain what was seen. Maybe 0.25 solar masses of blue ejecta that's moving rather fast, 0.3 c, and a larger mass of slower, 0.1 c, red ejecta that we see the combination of. So at early times we see mostly the blue thing producing this bump. As time evolves, we start to see sort of both of them, so we get kind of two bumps. And at later times we're seeing mostly the infrared emission, right? And then here's the kind of light curve. So the early kind of bright blue stuff would be powered by this blue component, and then the later stuff would be the red component.
Is the geometry very important?
It could be, yeah. And at this level, I mean, here we just took two spherical models and superimposed them. I'll show you more detail. Two separate sphere models. No, two separate ones. So we're not really treating the interaction of those things. I'll show you a calculation that sort of shows you some of the effects you can have. So this was sort of first pass in the first couple month or so after the event, but
So that means there were 4 newtons.
you could do it that way. If you had two mergers happening at the same time. No, probably it's some geometry where we're seeing both. But the interplay between the two is actually kind of fascinating and something that still needs to be looked at. You can overplot a model with the data. I show this because it's one of the most striking ones of this infrared spectra. This is sort of 1 to 2 microns in the black to one of the models that actually fits out better than maybe we even deserve, given the uncertainties and the all the isotomic lines and stuff. I mean, there is some robust physics that kind of sets the peaks here. You know, the fact that you sort of have a natural temperature scale and the scale of this. But that is quite convincing things. If you look at the spectra over time in the infrared, you can fit pretty well. But at some epochs, there's deviations here, right? This model doesn't fit quite well. So there's more work to be done to try to understand this. I'll skip ahead. There's some other interesting indications here of measured temperature that's sort of plateauing at this recombination temperature that we had predicted. So that's another nice indication. And what else do I have? And I have more to say, but I can, let's see, where should I skip to? Well, Rem is saying, yeah, but I'll say, you know, there's more work to be done in terms of what the interaction may look like. So the two components may have some interesting geometry. Maybe the red is, if the red was on the outer sides and the blue was in the interior, then, you know, there's some viewing angle dependence. If you're looking sort of on edge, you're going to block the blue emission by this heavy R process material around it. So there'll be some inclination dependence. You know, interestingly, the gravitational waves gives us some handle on the inclination, so we can have different observations where we observe things at different things. If we have a black hole neutron star going forward, well, things might look a little different. You basically tidally disrupt the neutron star. You don't really get much wind. You maybe get a little red wind and some tidal tail, but you probably don't get much shocked ejecta. So when the next event happens, they see a neutron star black hole, you know, the idea might be, well, maybe you won't see very much blue emission. You'll see mostly red tidal tail emission. And I'll stop. There's more I can go back to if there's questions on sort of what we can infer about the remnant and other things. But I'll just sort of end here by, you know, just kind of appealing to, you know, so how surprising it is the theory by, you know, many different aspects and many different groups kind of came together and go through all these different levels. I talked about sort of every stage here at the end of the day making some prediction of a kilonova. And all of this done was, you know, without really any observational input. It was just theorists trying to work out physics at the best of their ability. Lots of uncertainties along the way. And at the end of the day, it did rather well that you can do a complicated multi-physics problem and get something that looks a little bit like the observations. But now we're at the phase where we've jumped from, well, what's the basic picture to now we have an incredible data set. We need to do the deep dive and understand all the details going in and think about what the diversity of events are going to be going forward as hopefully we discover a lot more of these events. So I'll stop there, and if you have questions, we can go back and talk about more. Thank you.
Thank you, Dan.
Mm-hmm.
Right.
So, would you say that the presence of the blue emission necessarily implied that this was actually a double neutron star merger and not a black hole neutron star merger? But as you said, the particles came from the
Yeah,
waves.
yeah, right. So I can go to this, and this is, you know, so we see what we see, and we can infer to some extent trying to fit the light curves and the colors. We can try to infer, you know, how much mass was ejected in each component. And there's some uncertainty there, given the uncertainties there of, you know, factors of a couple. But then you can say, okay, well, we kind of roughly know how much red material and how much blue material. What does that say about the system? And so, you know, depending on how far you want to go interpretation, you can do. I made these sort of schematic diagrams that roughly, not in any quantitative way, but suggest how the ejected mass may depend upon different parameters, and so you can kind of see. So, yeah, is if I go to a very high mass ratio, which I might expect for a black hole neutron star, I expect this squeeze polar ejecta to become negligible because I don't have a collision of the neutron stars, but I can get a lot of tidal tail material because I'm basically ripping apart the neutron star. And so if you believe these simulations and our understanding, you could say, okay, the fact that we saw something maybe here would rule out a black hole. Now, if you have, I guess the simulation hasn't been done of two sort of equal mass black hole with a neutron star, since it's not a very motivated physical system. But my feeling is you would still lack this sort of squeezed ejecta as the two stars come together. So you might wind up just with this red component. You could try to say something also about the remnant as well, a hypermassive neutron star. Again, if it collapsed early, you don't get a lot of mass. As we showed I showed a plot. If the hypermassive neutron star lives longer, you can eject more wind. So that has been argued. Ben has a paper and other things that the merged remnant lasts as a hypermassive neutron star for some period of time, enough time to eject enough mass in the wind to explain that infrared emission, but not so long that you've got too much blue wind or dumped in a lot of energy from the spin down of the neutron star. So you can try to constrain the lifetime and such by such arguments. But all of these are not entirely, very quantitative. They're just suggestive.
You mentioned briefly the actinides.
Yeah.
Now the actinides are far more neutron-rich than the lanthanides. Do you think that production is a sort of a continuation of the heavier process, or because it needs a YE even more extremely low? Would it be a special kind of site or a special location or something like that?
Yeah. Yeah, you need even lower YE, more neutron rich. You can make it all the way up to the actinides. So sort of in the conditions of the tidal tails, you may make just about up to the actinides. But if you go, it depends how neutron rich you think those outflows are. You can make more or less actinides. So there, kind of as there was sort of a YE, kind of critical YE where you made it to the heavier R process. There's another even critical YE. Yeah, it's not quite as sharp, but there's a transition as you go lower. And interestingly, if you look at stars, the abundances in stars, there's some evidence for some stars are sort of actinide enhanced, so they have greater element abundance of actinides relative to other R processes like europium. So there's some indication from looking at the abundances in stars that maybe there's special conditions where you make actinides and other ones that you don't. And so you can all try to put it into whatever picture you want. Maybe the tidal tails can make actinides, but other aspects of the wind or something are not rich enough to make actinides. So depending upon where you are here, how much tidal material you make, maybe this makes actinides and this wind makes less. Different stories you could try to tell.
How sure are we about the final fraction of heavy elements, and what would be the most robust way to measure that?
Yeah, the fraction, the mass, or the different abundances. So the masses are based upon fitting. Whoops, I went the wrong way. Are fitting on the light curves. So a lot of people have fit these light curves in different ways. Where's my fit? Did I show a fit at some point? I guess I erased it, but in any case, you can. Well, here's an example. I'm not showing the fit to the data, but you can fit to the data, and the brightness in the infrared and blue, and this infers kind of numbers like this. Now, people have used these toy analytic models, basically exactly what I laid out in that worksheet to do the same kind of fits, and the numbers always kind of work out in this range. Now, I said this is a little uncomfortable. This fast blue, well, we think this is sort of the polar ejecta, but I showed you in the simulations you usually get about 1% maybe at most, and it seems like we need more here, and 1% was for very compact neutron stars, right? So again, if you like to overinterpret, you might say this is a indication that the equation of state is such that we have compact neutron stars to make that much. But some people might say, oh, this is a problem. There's more mass than we can explain. But I think given the uncertainties in these radioactive heating rates, in the sort of the geometry and distribution of ejecta that we're using, and the opacities that are based on all these lines, I think this number can float by factors of a couple. So I'm not so worried about it. But all these numbers are on the sort of high end of where you might expect. I don't know if that was your question. You can also ask, can I infer sort of detailed abundances of like how much, well, all the papers like to talk about the fact that there's gold here and platinum and all these heavy elements, but it's really the lanthanides that we're seeing, and it's hard to identify them. You see features. There's information here in the spectrum. but it's not like one line that we can say, okay, here's the gold. Can't do that, but what I try to do here is trying to change the abundances of, say, neodymium or cerium. And you can see it changes the position of peaks here. So there's information, there's a long-term program of understanding all the lines of these heavy elements and figuring out how do we interpret these spectra to get more detailed information about what we're seeing. And there's information there. It's just going to take time to figure out how to do the spectral analysis.
More questions? Come up.
You mentioned briefly the line smear deposition.
Yeah.
And
Oh.
from the 17 paper, they showed that the capacity is about 100 times larger than Kasen.
Yeah.
Can you say a few words about that?
Well, I'd love to. Yeah, it's a. Again, I had enough technical stuff I think yesterday, but this is good technical stuff because it was somewhat of a debate for a while where in this Fontes paper and Chris Fry and the Lano group were calculating opacities here. So these are expansion opacities, which they calculated, which is equivalent to what we had calculated, very high, 100, where electron scattering, your typical electron scattering in hydrogen's down here. And they were saying their opacities were even a factor of 100 higher than that, which was somewhat devastating to observers because this meant that the flux they predicted would shift all the way out of the infrared into the mid-infrared, maybe be at like 5 microns or something, which would be unobservable. This is all just the treatment of the lines, which I think is done incorrectly, and now you understand how opacities work. Right? Here's an opacity. The lines are very narrow, we showed, and the photons move from step to step. Path. So I like to use the analogy, this is like the forest. You go in the forest and close your eyes and start running. Your mean free path is the distance to the next tree, and then you'll hit it and you'll go another direction. And it doesn't really matter how big the tree is as long as it's a big tree. And that's what sets how your mean free path and how fast you get through the forest. The way they treated it is to say, well, I'm not going to count the number of strong lines. I'm going to smear these lines and give them some broadened Gaussian width. That is now, a couple hundred times, well, this is now 100 times what the actual thermal velocity is in the kilonova. And then they broadened it even more to something like this, so that the thermal velocities they were inferring were something like 10,000 kilometers per second instead of the real value, which is like 1 kilometer per second. And now the forest of trees has become a bunch of shrubbery. It's just and now you can imagine, the physics of what happens when you do this. Again, you're redshifting, but now everywhere you go, you take a step. You move slower through shrubbery than a forest, right? Maybe less painful, but you. What's that? These are centimeters. Yeah, I wrote I use kilometers per second. These are centimeters per second. That would be pretty fast. Yeah, this is 100. I think they even use 10 to the 8 centimeters per second. Yeah. Yeah, so this is 10 kilometers per second. The real value is, this is 1 kilometer per second. That's close to the real value. But all the lines they smeared out into sort of a continuum. And now every time you try to move through, you've closed all the windows. You can't go. Your mean free path is now tiny because you're always in resonance with the line. You've made your line so long, and that's why the opacity turns out to be 100 times larger. For what I would say is an unphysical reason. The lines are not Gaussian broadened. This is not a turbulent motion in the atmosphere. It's a homologous expansion. And the right description is the one we talked about as you move through. So that's my opinion. We've had some discussion about it. But I mean, the expansion opacity is still an approximation because we're just sort of taking the average spacing of the lines. You should really run a calculation where you resolve all these. It's just calculated. But I think it's a much better than this. This assumption where they took the lines that should look like this and impose some Gaussian width to them that spread it out into this. So all the lines blended together. And now you're always in resonance with the line instead of having a tight resonance point. And so that gives you a higher. So yeah, you've taken the peaks and you spread them out, but what matters is the windows between these peaks. That sets your mean free path. Now there's no more windows. You're always feeling the opacity of lines. You're scattering much slower. So that gives you much longer light curves and redder light curves, which was not so consistent with what was seen. So there's more details in terms of understanding all this opacity, but I think this was somewhat of a diversion in terms of understanding the transport physics. Important one now. Any other questions?
Flight time handy?
My
She's on the
flight
line. Flight number.
91, I think it was.
91.
I don't know if anyone's in my boat that their
Yeah,
flight
another
got
question.
canceled, you know. Yeah. It's very, I don't know if anyone on the East Coast, it's very snowy right now.
Yeah, so my
Yes.
question is about the last slide you show that the problem involves many different physics. So
Yeah.
my question is that which part of physics do you think have the largest uncertainty, and which part of physics maybe do you expect maybe large improvement in the near future?
Yeah, it's a good question. There's uncertainty in every step, and I think we've gone to this, it's sort of a weird situation where the theory had moved along to a fairly sophisticated level where it had a pretty detailed picture of what would happen in a kilonova, and it was sort of the point where, well, why work on details when we didn't even know if kilonova existed yet? And then all of a sudden the kilonova came and the data set was extraordinary. So now all those details start to matter. So what's the most important? I mean, at each stage there's crucial things here, right? I mean, here the treatment of neutrinos is sort of the cutting edge of can we really predict what the composition, what the YEs coming out here are? Do we really trust those? Is the neutrino physics in the simulation good enough? Here there's a lot of uncertainty in terms of the nuclear reactions and nuclear inputs in terms of the radioactive heating and the abundances we get out and the radioactivity. Here again, all the line opacity data, all the atomic data. We've been improving it, but it's still uncertain. And then of course there's some details I talked about with the radiation transport. As you go to later times, I mean, one of the interesting things now is they could follow the event went behind the sun after a couple weeks, somewhat mercifully, so as the data was getting too good, but they could have followed it for much longer, even to the nebular phase, and where a lot of the assumptions we make break down, and you might have cooling emission, and no one's really even studied what these things would look like at the late phases when you have an optically thin, non-equilibrium sort of thing. So there's work to be done there. So every stage, I think, needs work. But I think what the most exciting future will be is that this was one event. Probably the next event will look different for some reason. Maybe it's a black hole neutron star, maybe neutron stars of different masses, maybe different orientations. And so hopefully every time we see something, it'll have some different twist to it, and we can play the game of can we fit that into some coherent picture of the diversity of the event. And at the same time work on some of the nastier details of the theory. Of course, there may be some physics that is important that we just haven't thought about. Maybe we always have to be careful. We had this kind of working on this for years, so we had our own preconceptions of what should happen, but maybe there's other things going on that we don't know. So, I mean, maybe we think all the energy is coming from radioactivity, but some people have suggested, well, maybe there's a black hole or a neutron star in the center that's continuing to energize material over some longer period. What would that do? Or maybe there's some other physics we're not thinking about. And so I think we should keep an open mind in terms of the interpretation and what other interesting things could happen. But
Thank you very much.